My name is Salvador Jaime. I'm researcher at CIATEC in León, Mexico. Today I'm presenting our findings on the effect of the electrospinning process parameters on ion exchange membrane properties. Salinity gradient energy is an energy source obtained mainly from the difference in salt concentration in rivers and other bodies of water. Reverse electrodialysis, called also RED, is a technique that has been used to produce salinity gradient energy. The electrochemical and mechanical properties of the ion exchange membrane play a vital role in the electrical energy conversion process by RED. In particular, an ion exchange membrane in a RED setup has to have a high degree of ion selectivity, low electrical resistance, and low degree of swelling. The relationship between these characteristics of ion exchange membranes and their electrochemical and mechanical properties for RED application are summarized in this table. We can see that the properties all depend either directly or indirectly on the ion exchange capacity and degree of cross-linking ratio. These two membrane properties depend on the base material synthesis method and the experimental conditions. Recently, the key strategy for the improvement of these ion exchange membrane properties for RED was the synthesis of tailor-made membranes with special attention on new raw materials, new manufacturing methods, and new membrane geometries. In previous works, we demonstrate that the membrane properties can be improved using electrospinning as a manufacturing method, and this is due to the increase of ion exchange capacity and the decrease of swelling degree. Electrospinning is a technique where a polymer solution is forced through a nozzle that has a specific voltage applied. These electrospun materials show unique characteristics due to their nano-size structure, large specific surface area, and tunable porosity and wettability. The nanofibers properties and the overall membrane performance can be improved by controlling the fiber diameter, surface morphology, and the internal structure of the nanofibers. The present work studies the influence of various electrospinning parameters such as voltage, tip to collector distance, polymer flow velocity, humidity, and collector rotation speed on the ion exchange membrane properties. All membrane preparation and characterization methodologies can be found in the reference cited in this poster. Result tables present the impact of parameters in membrane properties. Specifically for anion exchange membrane, the best value for the perm selectivity and the electrical resistance were obtained with flow velocity of 0.225 ml/h, collector speed of 300 rpm, thickness below 100 microns. Reflow distillation pretreatment is also an important factor for yielding better performing membranes. On the other hand, for cation exchange membrane, the best value for the perm selectivity and electrical resistance were obtained with flow velocity of 0.1 ml/h, collector speed of 300 rpm, voltage 17 kV, humidity of 40%, and thickness below 100 microns. As a general conclusion, it was observed that low humidity conditions improve the synthesis process by promoting solvent evaporation and the formation of defect-free fibers. A high collector rotational velocity allows for a better distribution of the fibers and thus a more uniform final membrane. A membrane thickness below 100 microns also presents improved properties over thicker samples. Also, the flow velocity and the voltage should be maintained relatively low in order to minimize the presence of defects in the fibers. Finally, it can be said that the electrospinning technique is very promising for the synthesis of ion exchange membranes, giving them satisfactory characteristics for their operation in red applications.